Something's there. Let's see. Properties. So low. I don't know what the heck that is. How about that? Let's see if that does any better. Oh, that does way better. Okay, so let's. It doesn't pay to be prepared sometimes. So let me first mark the edges. First, let me do this. Let's see. Okay. You got the last erasing all the way over to, so about right here, all the way over to maybe right there. Maybe. Oh, a little further over. Okay. Maybe right there. Let's see. Oh, a little further even. Do we want the lights? Probably, the lights might not hurt. Yeah. Guess I'll take that back. So, chapter 13 is there are three portions of it. The first portion is just straight F is equal to MA in X, Y. Then there's a portion here, like that is F is equal to MA in polar. And then there's, how should I say it, multi F is equal to MA. That sounds weird, but what I'll do today is that one and that one. So the way they're listed in the book is this one, this one, and this one. I'll do this one and this one, and then I'll go back next time and do that one. So it sounds weird why they would list them that way. I would think it would be more natural to do that than that. So let me just go ahead and do a simple one here, and then we'll go do some of these. Because these are kind of cool, I think. This is one of the harder problems. These are kind of easy, but let's just take a simple block and let's say somebody's shoving it. We had that thing for friction back in statics, where force, usually it was listed like that, and it was mu normal. Now this could have been the static or dynamic. For example, if this is carpet, let's say the carpet, it'll kind of sink, this carpet's not that bad. But some carpet has a real deep pile, and your piece of furniture kind of sits in there. And once you get it going, it's easier to get it going after it goes. So if you look at it, what you might do, force, I'll just say force applied. So you might be forcing applied, and then all of a sudden it breaks free, and it does kind of like that. So you're pushing, nothing's happening. Then bang, it starts happening. Then after you've got it broke loose, it takes a little bit less. So this might mean that the dynamic friction, let's just make it for this problem. The static friction is maybe 0.3, and maybe it's 0.25. Probably wouldn't be that different, that far different, but it doesn't really matter. So let's say you had somebody pushing a crate. Let's make the crate piece of furniture. Let's make it just a piece of furniture. It's a piece of furniture. Somebody's shoving it here, has a weight here. It's maybe, most furniture six foot tall. It weighs 100 pounds. But if it's 6 foot tall, maybe what you're doing is you're pushing it the other way. You're pushing it like here. So you've got a component going this way. Say you've got force applied, and say this is such that this is a, here, 3, 4, and 5. So you put force applied here. That force applied should be listed here. And then what you get, put it up here, this would be 4/5 of the force applied, and this would be 3/5 of the force applied. Now, if you turn around and you said, I'm going to do a free body diagram, you would erase the carpet, and what you would do, you would put, you wouldn't know where to put it, so you might just put it here, a normal force, because it might be wanting to tilt, and then you would have something like that. So maybe I should make it simpler and then I'll make it, I'll keep this one, redraw it right here, and then I'll go back to that one. Let's make it simpler first. And let's say somebody just pushes it directly with the force applied. It's still 6 foot. Say they're applying it 3 foot up to the top. It's 100 pounds. And then we're just going to put this normal force over here for the time being. And then what we're going to do is we're going to put the force due to friction. And so the first question might be, how much or how hard do I have to push it in order to get it to go? So in this case, you do sum of the forces in the Y is equal to, actually, the mass times the acceleration in the Y. And that is going to be 0 because it's not going to jump off the ground or go through the ground. And so what you're going to get is 0 is equal to normal minus 100 pounds. So that's just going to tell you that's 100 pounds. Here, you're going to have here, I'll do it this way. Okay, so should do it, because I'll invade this problem, but then I can erase that. Sum of the forces in the X equal mass times the acceleration in the X. This time I might have some acceleration, but I don't know that for sure quite yet. So on the left, I'll carry this. I didn't talk about, this is it's 100 pounds, so the mass is equal to the 100 pounds divided by 32.2, that looks ugly, feet per second squared. So that'll be the mass that you'll put there, but we'll put it there in a minute. Sum of the forces in the X. I got this one, we got that one. So I'll put this one first, F applied, minus, I got 2 cases here. So I'm going to list both of them. The first one being 0.3 times that. So in other words, what I've got to be able to do on this particular problem is I've got to move it, okay, mu, I'll recopy that. And mu dynamic is equal to 0.25. So you push and push and push, and all of a sudden at 30 pounds, or force due to friction is equal to mu times normal, but that's 100. So for this one, you get 30 pounds. Once it broke free, it would be 25 pounds to keep it moving. So first of all, you got to push it with more than 30 pounds to get it started. Once it's started, it's just moving with the 25 pounds. Does that make sense? So it just kind of, so I filled both of these in, but I really shouldn't. This just gives me a guide that I got to have more than 30 pounds. So I haven't said anything that, and probably if I push something, I don't know, maybe I could push it at 50 pounds. So let's say I pushed it at 50 pounds. So if I pushed it at 50, the first thing you'd know is I would start, push it up here, and then pop, it would break free. But once it broke free, it started moving. I'll say this, moving, meaning their acceleration in x is not equal to 0. Static, meaning the acceleration of x is equal to 0. So right here is the static, and then over here is the dynamic. I should have said instead of moving, dynamic. So you push and push. I mean, you rarely instantly reach 50 pounds. So you start pushing, get to 30, breaks free, then you're moving. So actually, you got two of these that situations that could occur. If you got 50, whoops, that's a 50. And then now you got this, you've moved into the dynamics and you end up with 25. So your end result is 25 is equal to, now I can borrow that, 100 over 32.2, acceleration x, then you just get a number. So is equal to 32.2 times 25 divided by 100. And I've got, I've been playing influence with this app to do this. And it kind of works as long as my handwriting is good. So it copied it down right. Then it did 160 over 20. And it's got two different possibilities. One is 8.05. It's just the way it was listed. And so my acceleration is 8.05. So then somebody may ask the question, okay, after you push it for, 2 seconds, how far did it go? So let's say in 2 seconds, after you put your 50 pounds, how far did it go? What's funny is there never really is there's the assumption in these problems that things occur instantaneously, like here's my time, and all of a sudden I got 50 pounds. And that's not the case. Usually you push force on it, and then you break free, and then you're at 50 pounds. So there's a little bit of this gray area that there's never even really addressed in the book. But we're going to assume that the 50 pounds is instantly applied. And so if you've got an acceleration in the x equal to 8.05, it's constant because the f of x equal to a constant, which is partly what I was talking about that I didn't like, that actually, there's a gray area where you're pushing and all of a sudden you reach up to that point. But if the force is a constant, the acceleration is a constant, then you just get these equations. Plus acceleration x t squared over 2. And you maybe somebody's asking you the velocity, I don't know. But t plus acceleration xt. So these are for constants. If they were not constants, and maybe we'll come up, well, okay, so usually when the force is not a constant, they move to impact because the solution becomes a little easier to come by. So in this section of the book, they really don't do, time-dependent forces. They wait until you get to that section on impact, which there's a reason for that. We'll go through the reason for that. But in this case, if you started with velocity 0 and that position would just be 8.05 times t squared, which say for 2 seconds, over 2, roughly 16.1 feet. That's quite a bit. So if I didn't do anything wrong, that's it. Now after that, what would your velocity be? Velocity would be 8 times 2. It'd be the same thing. Acceleration x times t, which would be 8.02 times 2, which would be 16.1 feet per second. Nobody really addressed the fact that, and they don't address that, like if I'm pushing a piece of furniture and I'm pushing 50 pounds on it, if it breaks free and it gets away from me, I'm probably not going to be able to maintain that 50 pounds because I'm running. That's quite a bit of speed. I'm running across the carpet trying to push it, So again, you get this concept that you're, so. But this is partly in statics, but also in dynamics. And it kind of makes sense, especially if you've got something like carpet, it might happen. A lot of the problems in the book, he may give you the same value for these two. Like if it's like a piece of metal against a piece of wood, then the wood's not going to divot down like carpet would. If you think about a piece of carpet, it kind of pushes it down. That's kind of an extreme case. So you have to overcome this pushing it up over this or laying the carpet fibers over to get it moving. Wood and metal, things like that, that's not going to occur. Unless the metal is like, 2 tons and the piece of wood is a pound or something. But for the most part, that doesn't occur. So there's a lot of times that he'll give you these two, they're the same number. And so, So essentially, those are the grand expanse of these type of problems. They're fairly simple. The pictures might look different, but they're essentially going to be the same thing. The other question I didn't even address, and I should have addressed it before, would that piece of furniture tip over? Well, I did not draw the width of the thing. So here's what we'll say. How wide would it be so that it started moving without tipping? And so how would you solve that? I probably could fit it right here. So what I would do is I would assume my normal touch to the edge. And then what I would do is I would sum moments about, what would I call it, point A or something? I would sum the moments about that point A equaling to 0. Why is it 0? Because it's not tilting. Usually there might be some sort of acceleration, which later we may find out it's like that. Some inertial component, and then some acceleration component. But if it's not ever tilting, it's just stayed vertical, it's like that. And so then we take the moment here. This doesn't produce a moment. If the normal sits all the way at the edge, assuming that it's about to tip, then it doesn't have a moment. So you get a moment here and a moment here. So this moment here, I guess what I need to do is dictate what's positive. So this one will be a negative one because it's going that way. So it will be minus 3 times, I said that was 50. So that's 150. I can do that now. And this is 100 times the width over 2. 100 times the width over 2. So the question is, if this is too skinny, it's going to tip. What's too skinny? And so here, let's see. 150 equal to 2 over that gets you 50. And so the width is that. The width has to be about 3 or bigger for it not to tip. And so if it's 3, it's okay. If it's too skinny, meaning it's maybe 2.5, then essentially this becomes 2.5. Or say instead of 2.5, I can do the math there if it's 2. 2 divided by 2 is 100, and I get 150 minus 100, which means is not 0, which means it's starting to flip or tip or whatever you want to call it. So really, I should have done that, but I didn't. Really, that's kind of the first thing you should kind of look at, and so I was remiss in not doing that. I was getting too much into this stuff. And then I never even put the width of the piece of furniture up there. So that's the almost. I mean, I'll do one of these in a minute, but that pretty much covers most all of those, because there may be some without friction, and that's easy because then you don't even have to solve this. You just have some forces, and it starts moving to the right, and you basically don't have this friction force. And essentially it becomes 50 here, and then you just solve that and it gets moving faster. That's it. This one is a situation where, okay, I'm just going to say, I don't know, what should I make it? 70. No, I'll make it 100. So I'll make that 100. So if that's 100, and this is 100, which becomes 100 divided by 5 gives me 20 times that. This gives me 80, and this will give me 60. So now what do? All you're doing is, okay, sum of the forces in the y equals 0, equals to, why is it 0? Because it's not jumping off the ground or not going through the ground, so it's not accelerating in the y. And so and you know, I should have been doing that too. So I should be doing this as well to be. So I do that. I get, I don't know, which one do I do first? I'll do the 60 minus the 100. And then I get my normal, let's see, plus my normal. And so my normal, this time it's 40. I didn't put the friction force there. So now I've got two possible situations here. Over here, if I had my normal, I multiplied it times my 0.3 and my 0.25, it made this little diagram. Maybe I'll do that real quick here. So I got the same thing, except this time it's 0.3 times 40, which isn't that 12? Is that 12? No, wait a minute. Yeah, that's 12, isn't it? So that's 12. And 0.25 times 40. Oh, geez, what is that? Is that 10? 0.25 times. I think that's 10. So I got 10 pounds and then 12 pounds. So if I overcome or push more, obviously 80 is more than 12. So it's going to push it out, break it free, and then it's going to basically go to the right. So sum of the forces in the x is just equal to the mass and the acceleration in the x. Again, this is a different problem than that, but the setup is the same. So what I got is I got 80 to the right, and I got this friction holding me up, But I broke free at the 12, and then I started with that, and then I get the 100 over 32.2 acceleration of x. So now I get an acceleration of x equal to, I think that's 70, 32.2 over 100. And I'll see if this one can do it as well. Let's just see if I can actually get it in there. See if it first. Oh, it really, no, it said, okay, it thinks that's 160. It thinks that's 160. Let me fix that. Oh, now it thinks it's 100. 22.54. So, and then I can go through the process again. And so that's all these ones are. Like I said, the picture might look different. There might be friction, there might not be friction, there might be some weird stuff. That's essentially it. So now instead of me doing this one, I'll wait to that one for next time. Now do this one. What does that mean by multi? And that's pretty interesting if you look at it from this standpoint. And first I'll do it no friction. Okay, so because the no friction really helps simplify things in the first problem. So let's say you had a pulley, and then say, okay, go down here, and I go over this, and I connect back to here, and this is a pulley that's connected to a block. I think that all fits. I think that bar right there is yeah, it's all fitting on that. And then this time, it goes over to here and connects to a block like this. And this one's sitting, there's no friction here, there's no friction here. So these don't have friction. So let's say this is 10 kilograms. Let's say, I don't know, let's just throw a loop here, 10 kilograms. This is, okay, this looks like to me 45, and maybe this is 30 degrees. However, both of these angles are going to be in the way. Of course, I could do a free body diagram separate, so I'll just keep them there. So the fact is, I got multiple bodies. Now, he doesn't call it multi F is equal to ma. He calls it multi particles, which is not really a particle, but the blocks aren't rotating, so they're acting like particles. So if you look at this thing, it looks pretty much, give me a second here, it looks pretty much like you've got two independent problems that are kind of stuck together, not stuck, but tied together through that rope. Okay. So what I'll do is I'll split this. Oh, I guess I should complete this out. So this goes up and it's connected here. So this is so that's a pulley with a bearing right there. So first thing I'm going to do, I might as well do this. Do this and call it SA because that's the A. And then I'll go out here and call this one SB. And then your length of your rope is equal to the delta, the parts that are connected on the pulley here and on the pulley here, plus 2 times this, because there's 2 ropes right here, 2 times SA. And then one of these, because there's just the distance from here to here. Now, if you take one derivative, you get that, and it's nice. But if you take another derivative, you get this. 0 is equal to 2 SA double dot plus SB double dot. Now, there's a big key here. This is very, very important. And that is, this is positive this way because of the direction. And this is positive this way because of the direction from the datum to right there. So this is your datum. Your two datums there. And so the key is now, okay, now I've got to look at each individual block and look at it from that perspective. So that's why I called it that, although he'll call it something different. So take A, and I'll redraw it. Hang on a second. That's the 30 degree. So let me try to at least make it look 30 degrees. Okay, so that's 30 degrees. Okay, so over here, I have this, and I end up with 2 times the tension. Now the first thing is the pulley here and the pulley here have no mass. If they did, it would make it complicated, but you have no mass for these 2 pulleys. Turns out the tension in the rope is the same all the way through. So I can put 2T here and I can put a T over here. But I also have to do this. I have to, what did I say, it was 10 kilograms. So I have to do this. We're not having friction. So if I did, I would have to have this and some friction force, but I don't have that. So do I care about the normal? No, because I don't necessarily need to know much about it. I could tell you what the normal is so that the block doesn't leap off the plane or go through the plane. Past that, there's no real need to have that. So then the next question is, we'll call this plus X, and then we'll break this into 2 parts. The part we don't care about, like who cares? I don't care about that. This one I do, because I'm going to sum the forces equal mass times acceleration up this way. So then I said this was 30. And so that's 30. And so it turns out that's 10 kilograms. So this weight is equal to 10 times 9.81, or it's equal to 98.1 newtons. And usually I'll put it in TS, but I notice everybody else just puts it in, so I don't want to mess things up. So this part's going to be 98.1 times the sine of my 30. There it is. And so it turns out that's, I think sine of 30 is a half, but that doesn't matter. So here's the deal. I got my free body diagram. I got my normal. I don't care what the normal is because I don't have a friction force, but I know that force and that force offset each other. Big deal. Now I'm going to sum the forces in the X direction where that's positive. And I'm doing something on purpose, and I'm going to apologize, but hey. So there's my equation. So all I got to do is identify what's positive. I got 2T, and I got minus 98.1 sine of 30. And then I got my mass, which is still 10. And then I get my acceleration X. Now, I've done something to you on purpose, recognizing that this is positive here, but this is positive here. So, in fact, here, I better not write it here, I better write it over here. The acceleration X is equal to minus S A double dot. And why? Because this direction is opposite of that direction. So I can do one more step if I wanted to, and then I'll hold off on this 2t minus 98, you know what, just out of curiosity, let's see if it'll tell me. Okay. It should do it. Hmm? Oh, it won't do it. It's doing it in radians. That's wild. That's funny. Okay. So in the sine of 30, isn't that half? I think that's half, isn't it? Okay, so what's half of 98 point? Let's see, isn't that 48.05? Oh, 49. 49.5.
0.85 or 0.05.
Oh, okay, 0.05. Okay. So that's that equals to minus 10 SA double dot. So this is the equation I'm going to use all along with. So I don't know T and I don't know SA. So now I do this drawing for this one on the right. And it, I don't know, maybe I can put it right here. It's 45 degrees. So it's got a T this way. Now I'm going to mess with you because now I'm going to assume this to be positive. Okay, and then I got to weight, and that weight is 98.1 because it's 10 kilograms, like that one was 10 kilograms, they're both 10 kilograms. There's a portion that comes this way, which I could care less about because there's no friction. So yes, this will offset that. It'll tell me what normal is. If I had friction, I'd put the friction portion there. I don't have friction right now. And this one's going to be 98.1 over square root of 2 because that's 45 degrees. And that's 45 degrees. So now I'll sum the forces in the x direction, x being associated with this problem, whereas that's a different x, this is a different x as well. And it's going to be such that that direction down that way is positive, the mass times the acceleration of x. So I got this one, which is 98.1 over square root of 2 minus the tension is equal to, there's no other force, just got those two, 10 kilograms times the acceleration of x. Now, this acceleration is positive that way, which is the same way as this. So this means the acceleration in this equation is equal to plus SB double dot, which is that, you know, the SB double dot here. So now I can rewrite this, 98.1 over square root of 2 minus T is equal to 10 times SB double dot. Now I got an equation here. I got an equation here, I got an equation here, and I got an equation here. So what's funny is I can mess with this equation, SB is equal to minus 2 SA double dot, and I'll use this to replace this SB with the minus 2 SA, and so I get minus 20 SA double dot minus T and 98.1 over square root of 2. Suddenly, I realize I got an equation here with a T and an SA, and I got an equation here with a T and an SA. So a lot of times you'll see them in the book or in the work in the problems, they'll put them under each other. Minus T plus 98.1 over square root of 2 equals to minus 20 SA double dot. Now, depends on what you want to solve for. I can multiply the top equation times the minus 2, or I could multiply the bottom equation times 2. And if I did that, I would say minus 2, put a 2 right here, and I could change that to 40. And now I can just add these equations. This plus that gives you nothing. This one, 2, 98.1 over square root of 2 minus 49.05 equals to, okay, 40, that's 50. And that's 50 SA double dot. Just out of curiosity, I'm going to use it to try to find this. Let me see. I think I wrote it well enough for it to, yeah, false. No, that's not equal. This is a minus. Okay. That was an equal. Okay. 2, 98.1 square root of 2 minus 49. Okay. I think I got it. 89.68435. Now I'll divide by 50, and that should equal to SA double dot with a minus sign. Let me see if I can get it to solve that one. First, I got to make sure it's ready. Yeah. So I get SA double dot equaling to minus 1.793687, which to me, SA, to me means instead of it accelerating, I let loose of it, and then it accelerates that way instead of that way. So this guy pulls that one down that way. Does that make sense? So since it's minus, it's not moving that way, it's moving that way. So if you turn around, you should be able to take this, find SB double dot, SB double dot, yeah, is equal to 2 times that, which, which is, well, should I put that in there? Here, I'll read 2, 1.793687. I don't want to enter it, so I'm just going to do that, and it'll hopefully read it. That's weird. Okay. 3.587. So SB double dot is positive going that way. So the thing is going this way, and this thing is going that way. And then if you want to, you can find the tension, if you wanted to, if you felt like you wanted to. You can find the tension from either this one or that one. This one has less things in it. So I could take the tension over and bring that over. And so I have the tension equal to, now the tension is kind of cool. Okay, so look at the tension. Okay, I'm going to trade them. So 98.1 over square root of 2, hopefully it reads that, plus 20 times S, wait a minute, do I want to do, I've already written the 20, so I'm going to bring the SA over, and then it becomes a minus, so shoot, okay, minus 20 times 1.793687. Maybe it'll recognize it as 8. And so if I do that, let's see if I can back up far enough, and it gets the tension about equal to 33.49. Now, this one's interesting to look at. Here's why. If I went and held my hand here, there wouldn't be any movement. And then the tension of this rope would be offset by the weight over here. Now, I don't know that I ever actually found out that value. So if you had no acceleration, here, 98.1, that's not going to be read here. So 98.1 divided by square root of 2, what is that number? That number becomes, that number becomes 69.36. So if I held that, the voicemail, if I held this, it would be 69. If I let loose of it, it's going to drop to 33. Why? So why would it drop? Okay, the reason it would drop, and why does it, when is the case when it would increase? Okay, so think about this block here. It is not moving. So it's not moving right now, so that offsets that. So if I held the block, they would be equal. The tension would be 69. If the tension is less than 69, what direction is that block going to move? If this is less than that, it's got to go that way. If the tension was 80, that block would be moving that way. So the key is, if you start looking at this and you see this, you should be able to look at this and say, wait a minute, let's look at this and think about what often, and so if you have friction, this is the first mental step you take. Is you hold the thing and you figure out which way it's going to go, and then you work it. So this is what they mean by this is what I mean by multi. What they're going to do is multiple particle, and they'll put them in there and they'll say something. In the book, they'll say F(I) is equal to M, sum of the acceleration I, for I equal 1 to the number of particles. In my case, I just have 2. And in the most cases, you're just going to have 2. And you're going to have some way for the accelerations to be related to each other. Either rubber band or, in this case, it's more traditional. And that's pretty much it. I mean, these problems will be kind of hard, and so I'll remember to bring my extra part. We can get it to work. I may drive to the house in a minute and go get ready for the next class period. But because, especially since I have a problem in statics on this, that I don't know what happened to me. This stupid flu has knocked me for a loop. Nobody, did y'all ever get this flu? Don't need it, I'm telling you. I've heard word from some people who had it and had COVID and said it was worse than COVID. And I'm like, wow, man, it knocked me completely out for like 3 days. So I hope everything I said made sense, and if it didn't, there's a video on it. I hope the audio works. All right, I guess it did work.